Math 2414, Other Convergence Test Video 2, another example of the integral test. In the previous video, we introduced the integral test and we did an example. And as I mentioned, there are two parts of the integral test that can make it challenging. Number one is verifying that your function that defines the sequence that we're taking the sum of satisfies all three criteria. That the function is continuous, eventually positive, and eventually decreasing on the closed interval 1 to infinity, or wherever the series begins. So for example, if the series began at 2, then this interval would begin at 2. We just say 1 for convenience. But the other challenge is actually doing the integral and determining if it converges or diverges and concluding the same thing about the series. But in this example, all of that's going to be much easier. So I don't want you to think that it's always just a never-ending task. For this example, we're going to determine if the following series converges by the integral test, the sum from n equals 1 to infinity of 1 over n squared. This one will go a lot faster. For our answer, we first need to identify the function that defines the series. That's easy. Take the argument of the series, the 1 over n squared, replace the n with an x, call it your function. F of x equals 1 over x squared. And we do need to define the interval over which we're going to do all this on. Just start at the lower limit and go to infinity. Bracket, because we need all this to happen at the first number as well, at 1. All right, so let's talk about continuity real quick. We will type this up. Continuity. There's only one number that the function is discontinuous at. F of x is only discontinuous at x equals 0. Since that makes the denominator equal 0, which is excluded from our interval 1 to infinity. I'm just going to type I and F for infinity. Out. All right, so we're good with continuity. The only bad number isn't in our interval. As far as positive, well, I should say eventually positive, it should be pretty evident that it is. Because our function, excuse me, that's not what I meant to do. Okay, we'll leave it pink out here. Our function has a 1 on top, which is always, come on, draw it please, 1 on top and an x squared on bottom, both of which are always positive. So, lost that. So it should be pretty evident that our function is not only eventually positive, it's always positive when it's defined. The only place it's not defined is 0, so we're okay. So we will say that f of x is clearly positive on 1 to infinity. So not a whole lot to look at there. As far as eventually decreasing, it should be obvious that it is. Because as a fraction, the numerator is static, it's 1, and the denominator keeps growing as x grows, and therefore the fraction is decreasing from 1 to infinity. So this is, it's clear, but let's check the derivative just to verify. Because the derivative, assuming it doesn't misbehave, should be rock solid evidence that the function is decreasing. So a little bit of calculus 1. Let's take our function, 1 over x squared. Now some of you, to take the derivative, would use the quotient rule. And although that's not wrong, you should just write it as a negative exponent to the power rule. Our derivative is negative 2x cubed, excuse me, negative 2x negative 3, which is the same as negative 2 over x to the third. And remember, we're looking on the interval 1 to infinity. So what can we say? Well, when x is greater than or equal to 1, x cubed is positive, and the numerator is always negative. Negative divided by positive is always negative. Therefore, the derivative less than 0 on 1 to infinity. Therefore, our function is decreasing. It's not eventually decreasing, it's always decreasing. Not wrong to say it's eventually decreasing, but it never wasn't decreasing. Our function is decreasing on the interval 1 to infinity. So So the derivative there wasn't too bad. It wasn't too hard to figure out that it's always negative on our desired interval. Okay, so all the criteria are met. I don't know why I have a dangling comma down there. This, come on. Inside the text box, please. Thank you. Check that the function's derivative is less than 0 and negative on 1 to infinity, and just say that it is. We did the verification on it. All right, so we can do the integral test, which means we can check convergence of the series by checking convergence of the improper integral. So let's set up that integral. We're integrating, if I can get it to draw, we're integrating from 1 to infinity, our lower and upper limits on our sum, of our function, which was 1 over x squared dx. And by now you should know that, number one, this should become a limit to infinity, integral from 1 to t. And to integrate 1 over x squared, you should write it as x to the negative 2. And this is a pretty straight shot to the end. Limit as t approaches infinity. The antiderivative of x to the negative 2 is negative 1x to the negative 1. And we're evaluating this from 1 to t. Just to make it a little bit easier to see, let's write negative 1 times x to the negative 1 as negative 1 over x, because that's all it is, 1 to t. That's equal to the limit as t approaches infinity. Substitute the upper limit to get negative 1 over t. And then minus, but then it's going to be minus or plus. Substitute the lower limit, 1 over 1. Do you know what this limit equals? It could be pretty transparent. The numerator stays negative 1. The denominator blows up, which means that limit is 0. But we also have the plus 1 over 1, so that limit's equal to 1. And more importantly, integral converges. Because the integral test says under the right conditions, integral will converge if and only if the sum will converge. Therefore, the sum from n equals 1 to infinity of 1 over n squared converges. Now, it's important to point out that the integral test does not tell us what the sum converges to. It simply answers the question, do you converge? So when we got an answer of 1 back here, that was the value of the integral, but it's not the value of the sum. If you're really interested in knowing how the value of the integral relates to the actual sum, I recommend that you look in our textbook. So if you're my student, look in section 8.3 and look at question, it's either 33 or 34, where they take you down a path that shows you how the value of the integral can be used to approximate the sum. But for our purposes, we're simply going to use the integral to answer the question, does the sum converge? And in this case, it does. All right, we're going to do one more short video about the integral test, sort of, but more importantly about series that look like this, where you have the reciprocal of a power. Because just like the harmonic series, they are very predictable depending on what that power is.